Thank you for joining us from wherever you're coming in today. Recognizing some of the challenges we've had with snow and weather, it's nice to still be able to do these remotely. So my name's Tim Southerns. I'm the President and CEO of Digital Water Solutions. Thrilled to have you here today to attend the webinar on using AI and ML for leak detection in water systems. I'm joined today by Stan Fong, our CTO. Stan will be leading us through how Digital Water Solutions in particular is using AI and ML for leak detection, but also providing an overview and a quick case study for you. We expect that the webinar will last about 20 minutes of presentation, followed by the opportunity for questions and answers. I would ask that you use the Q&A button in the webinar to enter any questions you may have, and at the end of the presentation, we will walk through those and get Stan's expert opinion on some of the questions you may have, either from the content of what is discussed today or other questions you may have around the implementation of digital solutions in your water network. So again, thank you very much for attending today. We look forward to the discussion that'll follow from the presentation. And at this point, Stan, I'm going to turn it over to you to share your screen and lead us through this discussion. So thank you again.
All right. Thanks, Tim. Thanks, everybody, for taking the time to listen in today. Good morning, good afternoon, hopefully not good evening. All right. So as Tim said, today's webinar is on AI ML for detecting leaks in water distribution networks. In the past, we've done a few of these. We focused on things like PVC. We focused on other aspects of our technology, such as it being autonomous. Today, I want to talk specifically about pre-existing leaks and how we use machine learning to help us with that problem that we have in utilities right now. So most of you are probably familiar with the baseline approach when it comes to acoustic leak detection, right? You have acoustic noise from sensors you deploy across your network, and you use that noise as essentially a surrogate for leak activity, right? So let's say you start monitoring here, you take this first bit of noise as your baseline, and you set some threshold corresponding to that, right? Then when a leak happens, that noise is going to jump, and obviously that leak crosses that threshold. So then we would consider that as a leak being detected by the system. You'd go and repair that leak and move on. The problem with this, though, is this baseline, right? And where you take this baseline. So the main issue is, let's say I extend this timeline a little further back, right? This is that same baseline we have. That's the new leak. That's the start of monitoring. You can see here that actually in this case, there's actually a leak that started before we installed these sensors, right? And that is actually part of the baseline. That leak is included in this baseline. The true baseline, if we want to assume that there's no leaks at this point in time, is back here. So you can see what happens here is if that pre-existing leak is going to be included in this baseline, it's going to remain undetected for as long as you monitor, or maybe until that leak progresses to a point where it does correspond or correlate to that jump in acoustic noise. So what does that translate to in terms of your non-revenue water? This is the same timeline, right? So we've got, again, the start of monitoring, the start of that new leak, the repair of the new leak. You can see when that new leak starts, you're obviously going to have a jump in that non-revenue water. But then once you repair it, you're assuming it's just all corresponding to that one leak, you're going to return to that baseline non-revenue water. But you can see this is the fraction that you can recover through baseline monitoring and any new leaks as well. So if you have, this chart grows beyond this baseline, you can probably recover a lot of those leaks through baseline monitoring, but this fraction remains unrecoverable, right? And in some cases, this fraction is actually quite a large portion of the non-revenue water that you're tackling, especially if you've got pipes 60 plus years old. You really want to have a technology that's able to help you reconcile this piece of NRW. So there's a bunch of things that we can use machine learning for to help us with this problem, right? We know that when a leak happens in a system, it's going to emit a certain set of frequencies, and that depends on the pipe material. It depends on the type of leak, the crack geometry. It depends how far you are away from the leak. So we as humans, right, we can look at these, we can look at the data, and we can determine if there are some telltale signs or relationships that we can use to identify leaks from just the ambient noise in the distribution network. So what I'm showing you here, this is a frequency representation of the acoustic data. So on the x-axis, we have the frequencies from 50 to 300, excuse me. And then on the y-axis, we have the relative loudness. So when you have all these frequencies present in the data, how loud is each frequency relative to all the other frequencies? So we can see in a distribution system without a leak, you still have quite a bit of noise in this 50 to 100 hertz range. And then as you kind of go up that frequency spectrum, it's going to taper down to basically zero. And this is plastic here, but again, not too important. This also applies to metal as well. You might just get more higher frequencies due to the metallic being more transmissible. So this is what it looks like when you have a leak. So what do we notice? Differences, we can see here the peak shifts towards the right. So we can see for two different flow rates here, right, that leak frequency, or the set of leak frequencies really manifests around 75 to 100 hertz. Right, so it's going to shift that peak that used to be about just above 50 to 75 to 75 to 100. And we can see some differences depending on the larger flow rate. 20 here, the brighter red, is going to have a slightly higher frequency peak, right? That's just one example. Here it is in metallic pipe. So we can see the blue here is the baseline, right? Almost no energy in these higher frequencies. And then when a leak happens, quite a few frequencies light up, right? The same ones that we see in PVC, and then as well as in this higher frequency range, 300 to 400, 600 to 1,000 hertz. And we can also understand the effect of distance on those leak frequencies. So again, using that same kind of reference image here for non-leak. Here we have a bunch of different cases. So we've got 10, 20, 30. We have two different leak locations. And this is just to illustrate how those frequency spectra change depending on just purely distance, right? This is distance and flow rate. We can see different frequencies light up, or depending on if that leak is close by, even in PVC, you might be able to capture some of these higher frequencies. So the point I'm trying to make is, there are definitely relationships and features, as we call them in machine learning, that we can use to identify leaks and to differentiate leaks from baseline data. But there's also quite a few different cases we need to capture, right? It's not really just a black and white, if we see this frequency, it's a leak. There's a lot of variability there, and that's really where machine learning comes in. So what we've done is basically, we want to leverage machine learning to do a few things here. One is we apply it to the acoustic data to find not only all these relationships, or as many of these relationships as we can, but to identify the best ones. So that also means not just uh, finding, the most leaks, but also balancing that with reducing the false positive rate, right? We want to have a model that is able to basically provide you with the best of both worlds in that sense, and machine learning does a really good job at that. Secondly, it enables us to find these leaks directly, right, as opposed to relying on that change. So the problem of baseline methods needing that change or that jump in noise, because we are looking for these inherent characteristics, what we call fingerprinting, or the fingerprint of these leaks, and we're able to tell you essentially from day one if you have this leak or not. And then the second thing, or the third thing, sorry, is to be able to differentiate between different types of leaks. This is not as important as the first two, but as we kind of use the model over time, it's going to be able to build on that foundation. It's going to be able to tell us more and more about these leaks. Eventually things about if the leak is growing, what the flow rate of the leak might be. These are not things that we can do today, the flow rate specifically. But the idea is these models continue to learn. And the more information that it can tell us, the more informed you can be when you make a decision as to which leaks you tackle and, prioritization of those resources. So this is just to show, we take all those relationships, right? And machine learning is going to find a lot more of those relationships, a lot more of those features. And we have what we call the leak fingerprinting model. And so this is what we use to find pre-existing leaks. And now we'll dive into an example. So this is a fairly recent example. This is King County in Washington, USA. And in January 2025, they finished the installation of 5 units in this area here, right? So you can see 1, 2, 3, 4, 5. And the timeline goes like this. So the units are installed, they collect data. Our team looks at that data, runs it through that pre-existing leak detection. And what we determined was there's probably one or more pre-existing leaks in this area. So on the 22nd of January, KC was made aware of those leaks. On the 29th, we were able to provide them with precise location information as to one of those leaks, the more prominent one. And then the leak was repaired on the 12th of February. Right, so the leak location is actually right here. You can see that's the leak there. It's actually a leak close to an existing repair. So what are we seeing? So actually, if we kind of go back to looking at the frequency information, right, looking at this hydrant here, this is very close to the leak, right? We can see those peaks. So in this example, we can actually see, because it's so close to the leak, we can see the peak actually above 100 hertz. You can see another peak here, above 200 to 250. Yeah, and this is what the machine learning flags. These are some of the example fingerprint characteristics that it will look for. On 0004 here, we can see the peak is actually right about where that textbook example was, right? Between 75 and 100. And we get some chatter up here. So really, we could look at this and we could even interpret it ourselves and just say, like, this is telling us that the leak is probably closer to this hydrant than this one, which is what we told KC. And from that, over time, as we look at that data come in, we're able to provide a location. Before we get to location, we can also look at a different representation here. We know that these leaks don't just appear and disappear, right? They're consistent over time. So if we look at the top plot here, the y-axis here is the frequency. The color represents the energy, so purple being the highest energy, and then time on the x-axis here. And we can see that frequency band, right? So corresponding to that first hydrant, you've got a solid purple band here corresponding to the band of leak frequencies. You've got some blue surrounding it. And actually what we can see is that leak energy start to slowly creep up over time, right? There might be a small jump here, but we can see that slow trend. So this is something we can tell you now, right? When we find a leak, we can keep tabs on it. We can tell you which leaks are going to be stable, which ones start to grow. And if they suddenly grow, we can tell you about that. So we identify that leak and then we're able to provide a location. And this is essentially the heat map we provided. Didn't look this pretty when we provided it to KC, but we gave them two things. We gave them a pin of where we think the most probable leak location is. And we basically gave them an area to search, if it's not at that pin. So start here and basically look radially outward from this location until you find it. Luckily, the actual location of the leak was right here, right? So not too far from that pin. Yeah, and there's also the possibility that there's more than one leak in this area, right? So it's an iterative process where, when they find that one leak, they repair it, we reevaluate to see if there's still pre-existing leak activity, and then we can point them to the next leak, right? So we're in the process of doing that now. Here's a video, we'll see if it plays. Right, that's the leak. That's the repair. And what we're also trying to do right now is just work with Casey to see if we can determine some ROI pertaining to the leak. Right, so we know the pressure in that pipe. I don't think we have exact measurements or pictures of the leak itself, the crack geometry, but we can estimate that, and then we can put together some scenarios, right? Because we don't know how long this leak was running for prior to the installation of these units, but um, we can do some forecasting there and just throw out some scenarios to get an idea of was this worth it to fix, how much water was lost, and eventually we'll have this baked in to all the leaks that we show you in the UI. Apart from that, we also showed Casey a couple other locations where there might be some leak activity. This one here is on the other side of that pilot area. And you can see some is in italic here. There's some evidence of a pre-existing leak, but this is not one where we'd say you go out and do a sweep and dig. This is that reference example from before about that leak, that peak we expect to see at 75 to 100, but you can see it's not very consistent. Here, it's not as prominent. So this is one where we just want to make you aware of it. and we'll let you know if there is some development there. That's it. Definitely a big thank you to King County for allowing us to share their story with you today. Thank you everybody for taking the time to listen in. And if you're interested, you can check out our site here for more information or get in touch directly with Barclay or myself. And Tim, back to you for questions.
Great. Thanks, Stan. Really appreciate that. It's always interesting to see how the water utilities are able to identify the pre-existing leaks as well as getting information on leaks as they grow in their system. So I'll just go through a few questions here, Stan. The first one, it says, you use the term, we find your leak. I'm not sure it's we as in individual humans find the leak. Perhaps you would like to just give a little explanation as to how the solution works in terms of detecting a leak, localizing the leak, putting that out in front of the water utility.
Yeah, so that well, there's two layers to it, right? I think with machine learning, it's important to involve people in the process, right? So you as a decision maker, it's important that you understand how the machine learning models are giving you the results that you're seeing, and that's why we're happy to share some of this process, right? What's going into the model, why it thinks that there's a leak, and for us too, in the beginning, the pre-existing leak detection, that leak fingerprinting, someone from our team does review that, right? We want to make sure that we agree with what the model is saying, um, and so that's what we mean when we say we, right? The model is going to output us essentially this report. We're going to be able to look at that and determine whether we agree, disagree, and then we'll be able to tell you that information. That when we say we, it's also we when we start a pilot, right? Tim, typically Tim, sometimes I join in. We have these recurring meetings with you, right, every month to basically walk you through the process of using the technology, lay out those KPIs, and get you familiar with, how you can best utilize, right? So in that first meeting is when we actually told KC, here's what we found with the pre-existing leak detection. Now, the day-to-day leak detection after that, that is pretty much automated, right? Once the model is set up, it's just going to make its own decisions every day. We may periodically review that to make sure that the models are functioning as intended, but that is designed to be a system that just self-regulates.
Great, thanks, Stan. Yeah, I think it's always interesting for people when we think about technology, how much human intervention is required, and I think it's important for people to understand that when we do that pre-existing leak, we do a manual review of the model output to try to make sure that it aligns as we would expect and work it through with the water utility. Certainly, the nice thing about the day-to-day after that is the notifications and that show up on the map, and people can go out and actually look at the areas and see what they find in the field. So appreciate that feedback. Next question we have here, is this an add-on service or does it come with the purchase of the equipment? So I think I'll tackle that one, Stan. No, all of the things that Stan has demonstrated today are part of the hydrant.AI offering, and it does come standard with the purchase of the equipment. So this is all included with the units. The units themselves have 3 sensors in them. They have a hydrophone for listening to the water column. They have a pressure transducer for picking up pressures, but also transient pressure waveforms. And they have a temperature sensor for tracking the temperature of the water. In addition to leak detection and the models that run on leaks, there are also anomaly models that run on pressure for the water utilities as well to help them identify other issues with their system. So thank you for that question. Stan, another question here. How does the data actually get from the units in the field back to where we run our models?
Yeah, so the units communicate via cellular, right? So they're going to collect data every day. So pressure data is collected pretty much continuously, temperature data periodically, but acoustic data is going to be collected during that nighttime period. And then that data gets transmitted back to us via LTE. And then the models run each morning on the acoustic data, and your dashboard's hopefully updated before you get into work, right? So we're targeting 6 a.m. roughly local time to get you those results so that when you flip on that dashboard, you have the present day's information.
Great. And just to add to that, You can also choose to get alerted by text or email or both. And so if you like to be disturbed at all hours, by all means, we can help you with that as well, if the system requires it. Thanks for that answer, Stan. Question here, when you're communicating the data, how frequently are you sending that up to the cloud? Is this once a day, half every 12 hours? What do you typically recommend for people?
Yeah, I think now we have set to about once an hour, anywhere between 30 minutes to an hour. It's going to communicate and send all the data it's collected in that interval. If you have something like a pressure transient, it's going to tell you right away. So it's not going to wait for the next 30-minute interval because that's typically corresponding to something like a break. So you want to know as soon as possible. So it's going to override that connection interval and tell you.
Yeah, great. Thanks, Dan. Last question here before we let people go. Question about cost structure. So there are two models with which the units are actually available to water utilities. One is by using your capital budget to actually purchase the hardware sensors. And then there is a recurring software fee, a SaaS fee. And the second is to engage us with a data as a service offering where we maintain ownership of the hardware and make sure that it stays up and running for you. And then you pay a higher monthly fee for that service. So two ways to go to market. We know, having been in the water business for over 30 years, fully understand the difference between operational and capital markets. On that note, thank you so much for giving us the 30 minutes today to spend time with you. This recording will be available for you. We will make it available and send out a link. But if there are any follow-up questions, as Stan said, he's happy to connect with you, or you can reach out to Barclay. He's happy to talk through some of the costing questions you might have. And with that, thank you so much for attending.